All right, let's get into it. We use databases for, well, pretty much everything these days. Banking, social media, you name it. But what is actually happening inside that black box when you hit save? We're going to follow the secret journey your data takes and pull back the curtain on the magic that keeps it all safe.
It feels totally instant, right? You click that button and boom, your order's confirmed. But in that tiny fraction of a second, this incredibly complex and really carefully choreographed dance kicks off inside the database. It's a whole process just to make sure your purchase is recorded permanently, and more importantly, safely.
Now, to understand this dance, we first have to talk about the stage it happens on, your computer's memory, or RAM. And here's the thing you gotta remember. This is a finite resource. So for our example, let's just say our server has 16 gigabytes of RAM. The key is it has to share this one pool of memory with everything else that's running. So that 16 gigs gets carved up. The operating system needs it sliced to run, of course. Maybe you have an application like SAP taking a huge chunk, and then our database, we'll use Oracle here. It gets its own dedicated 6 gigabyte slice to play in. This little reserved area of memory, that is the database's entire world. This active running part of the database, the part that's actually doing stuff inside its slice of memory, that's what we call an instance. It's not just some dead file sitting on a hard drive. This is the living, breathing brain of the whole operation. So what exactly makes up an instance? So what is an instance? Well, think of it as two things coming together. First, you've got that dedicated memory we just talked about. That's called the SGA. And second, you've got a whole team of active background processes, the workers. It's the memory plus the workers that makes a database truly come alive. And really, this is the core concept right here. You take that reserved RAM, the SGA, you add those worker processes, and that's what equals a living database. You have to have both. Without them, the data files on the disk are, well, they're just unreadable, useless text. Okay, so our database instance is up and running. It's alive. Now let's follow a single piece of data, say a brand new sales order, and watch it take its very first steps into this digital world. The second that sales order gets created, two things happen at the exact same time. The data itself, the actual order details, lands in a memory area called the buffer cache. And, simultaneously, a little note describing this change, kind of like an entry in a ship's log, is placed in a different memory area, the redo log buffer. You notice the key detail here? It's all happening in RAM. Nothing's permanent yet. Now look, keeping data in RAM is super fast, but it's also really risky. So the database has these two special processes, and their only job is to write this temporary data to a permanent disk. So let's meet our main characters in this story. On one side, you've got the database writer, or DB writer. Just think of it like an efficient librarian. It's lazy in a smart way. It waits until there's a decent pile of books before it goes and shelves them all at once. It only writes when the buffer gets full or at specific times. But then you have the log writer. This guy is our aggressive scribe. He is not lazy. He writes down the record of the change almost instantly, the second you hit commit, or every 3 seconds, no matter what. He is way, way more cautious. And this brings us to the multi-million-dollar question. Our new sales order data is just sitting there in the librarian's temporary pile in RAM. It hasn't been written to the permanent disk yet. So what happens if someone trips over the power cord and the server just dies? Is that order gone forever? The answer is, yeah, kind of terrifying. RAM is volatile, and volatile is just a fancy word that means it needs constant power to hold information. The second the power is cut, everything in RAM, including our sales order sitting in the buffer cache, is completely wiped out. Poof, it's gone. And this is the absolute genius of the system. Remember our paranoid friend, the aggressive scribe? The log writer has already written the record of our transaction to a permanent file on the disk. So yeah, the data itself might have vanished from RAM, but the log of what happened is totally safe. And as long as that log exists, the database can automatically replay the transaction when the power comes back on and bring your data right back. Your database is safe because your log is safe. So we've nailed down safety. That's huge. But a database also has to be fast, right? The system has another really clever trick up its sleeve, and this one uses another part of its memory to avoid doing the same work over and over again. This area is called the shared pool, and you can just think of it as the database's short-term memory. See, Every time you ask the database for information, it has to check your query to make sure it's valid. The shared pool remembers these queries, so if you or anybody else runs that exact same query again, the database says, "Hey, I've seen this before," and it just skips the check and grabs the answer. That's why a bigger shared pool almost always means a much, much faster database. We've met our writers, the librarian, and the scribe, but they're really just part of a bigger team, a whole squad of mandatory processes working tirelessly behind the scenes. These are the unsung heroes that keep the whole show running. So let's do a quick roll call of the rest of the team. We already know our librarian, DBW, and our scribe, LGWR. But then you've got CKPT, who's like the conductor, making sure all the file headers are in sync. If a crash does happen, SMON, the paramedic, is the one that jumps in to do that automatic recovery we talked about. And watching over all of them is PMON, the supervisor, whose job is just to make sure every other process is alive and doing its job. So here's the bottom line. This whole system, this intricate dance of specialized memory areas and coordinated worker processes, it isn't complex just for the sake of being complex. Every single piece is designed with two fundamental goals in mind: making sure your data is never ever lost, and making sure it's always available the very second you need it. So we've pulled back the curtain on this incredible system that guarantees your data is safe. But safety is only half the battle. The next big question is, how does a database manage to sift through billions, maybe trillions of records to find the exact thing you're looking for in less than a second? What's the secret to its speed? Well, we'll get